Hello, my name is Anne-Flore, and today I want to talk about using educational theories of cognitive load as conceptual lenses for visualization design and evaluation. So cognitive load is a shared concept between visualization and learning sciences. We all operate under the same assumption that people have a limited amount of cognitive resources that they can dedicate to acquire information. This amount is highly individual and it can change for a given person if you're tired, if you haven't slept well, for example. If the load is too high, information is lost. Learning does not occur effectively. But cognitive load theory actually breaks down this notion of cognitive load into subcomponents, and today I'm going to talk about two of them. First, I'll talk about intrinsic load, which relates to the complexity of the information to learn in itself. And extraneous load, in contrast, relates to the way the information is presented and the learning activity that you have to perform in order to acquire knowledge. So I'll use an example to clarify, and I will start with intrinsic load. Let's say I want you to learn this piece of knowledge. In 75 years, because of climate change, the heat humidity risk to human health will increase in frequency and spread across the planet. So let's consider how many pieces of information I want you to process at the same time. So that's probably manageable, but only if you know what this means. I don't know if everybody in this room knows what it means, so we're going to unpack these 6 words. To understand what heat humidity risk is, you need to know that the human body needs to stay at 37 Celsius degrees. When it's too hot, we sweat to cool down. And the way that it works is that sweat evaporates into the air, thus cooling down the skin. But if the air is too humid, sweat cannot evaporate, so you cannot cool down. So you can overheat, and this is very dangerous. You could die from it. So if you don't know what heat humidity risk to human health means, this is all additional information that I need to give you in order for you to understand the overall knowledge piece that I'm trying to transfer to you. And this is what knowledge does actually, right? It encapsulates information so that we can process a higher level piece of information without having to keep in mind all of the subcomponents at the same time, thus reducing intrinsic load. Increasing the learner's knowledge is the only way that you can reduce intrinsic load. Well, you can also choose to change your goal, aim for something easier. And in visualization, intrinsic load is of course related to the learner's domain knowledge, right? And also to how complex the relevant data relationships are. The more variables interact, or the more data points there are, the harder it becomes to process everything at once. For example, going back to my learning goal, one data dimension will be the frequency of dangerous heat humidity conditions. Another will be the location where it happened, the area that is spreading. And I also have some sort of comparison to make between a historical baseline and one or multiple global warming scenario, so that I know that this is due to climate change and this will happen in that many years, not right now. So the viewer will need to coordinate 3 variables at the same time, and that's intrinsic. From now on, whatever I do, once I start encoding this visually, I'm adding extraneous load. Even if I build the most perfect visualization, there is still some effort for the viewer to decode that information, and that is extraneous. For example, I could build a color scale for frequency. Then I could decide to use a map for showing the area. And I could make multiple small maps to allow comparison. And now a vis designer like me could come and tell you, look, this is great. We can get additional insights. We can learn that tropical areas are especially vulnerable. This is so cool. But looking back at my learning goal, this is actually extraneous information. And now I wonder whether or not using a geographical projection was the right choice for this specific learning goal. And you can probably all think of cases where you saw a communicative visualization or learning material where there was extraneous information present. For example, in the document from which I extracted this visualization, if I wanted it to use for my learning goal, there is a lot of text that isn't useful at all. And what's worse, explanations are scattered around. You have some as annotation near the visualization, and others are in the text of the caption at the bottom of the page. A caption I have to read because this is where I learned that this is a projection for the end of this century. So this is another example of unnecessary effort for my specific goal. And visualization researchers have many insights into what generates extraneous load. They have studied extensively encoding's efficiency. They work on understanding and improving visualization literacy. We have seminar principles that teach us to avoid all irrelevant information, yet we still often struggle to do so. We think of layout a lot. All of this, I would broadly encompass it under the umbrella concept of readability. And in our paper, we present a short study that established correlation between perceived readability and extraneous load. But visualization systems are not just static, they also embed interactive features, which can support or hinder the learner's effort. For example, when you add a filtering feature in your system, you allow the person to reduce the number of data points to the ones that are relevant, thus reducing extraneous load. But we can also design them to support relevant processing load. For example, that's what we did in our study. We segmented the visual representation to let the learner manage the pace at which they would receive and process information. And by the way, that's also one of the things that data comics do. It doesn't have to be interactive, but this is an interactive application of the segmenting principle. This principle is described in the multimedia learning theoretical framework. There are many more theory-based design principles that can directly apply to visualization design and evaluation in this framework, and not just for educational context. These are the learning science theoretical framework that I've been talking about during this talk, and I think that visualization research can provide a fruitful testing ground for such theories, of course, but what's more, I really think that we, visualization researchers, we can contribute back to this framework. We can help refine and expand them. But to do so, we need to incorporate this concept as they are, and we need to use this vocabulary in our work so we can facilitate bridges between the two research domains. So that was my talk. Thank you very much.